Okay, let's talk about sampling rate. This is a term we use, we throw around a lot in the lab. We use the symbol FS to represent the sampling rate. And anytime I'm writing MATLAB code, I use that as the sample rate. Sometimes I'll use FSGRF, meaning I have a special sample rate for my ground reaction force. In MATLAB, I would do that, but for now, I'm going to write the units or hertz, representing samples, 1,000, sorry, running out of room, samples per second. Hertz is anything over seconds. That says samples if you can't read that. I can't read it. So if I can't read it, you can't read it, but that's what it says. Hertz, anything, almost anything per second, okay? Frames per second, samples per second, strides per second, hertz. All right, so sometimes we have instruments that are set to a high sample rate, like 1,000 hertz, or maybe we have motion capture. I'll just use MC for mocap. Maybe we set that to 200 hertz, 200 frames per second. Or maybe we have some other instrument that only samples 10 hertz, 10 samples per second. All right. And we even have some instruments that may only sample at 1 hertz. 1 sample per second. So obviously these are quite different in terms of what they're doing, but this one obviously is recording 1,000 rows of data every second. So if we turn our system on and record data for 10 seconds, that's 10,000 rows of data for the 10 seconds. This is recording 200 data points for every second. So 2,000 data points for 10 seconds. This is only recording 10 data points for 10 seconds, or 10 per second. So that would be 100 data points. This is only 10 data points for the 10 seconds, 1 sample every second. So in terms of storage, if we're using 1,000 hertz, we better be ready to be able to store those data points in our system. Now, for a lot of the types of data collections that we use 1,000 hertz for, we may only collect for maybe 5 seconds. But a 1 second type of sample rate, like a watch, not a watch, a GPS watch, okay, which is recording GPS data. Typically, these watches record 1 sample every second. So now I can leave the watch on for 10 hours, 16 hours. And the number of data points is a little bit more reasonable than trying to deal with 1,000 hertz. Well, why would we want to collect at 1,000 hertz? And why would we want to collect at 100 hertz other than a number of data points that we're trying to save? All right, that's what we need to understand when we're looking at sampling rate. Okay, so let's see. So sampling rate. And I should even say with motion capture, back in the day when we actually did have to use film or maybe even videotape, there was actually a cost to having too many pictures recorded. And so it was a physical cost of the film. And it was also, back in the day, we would have to hand digitize every frame. And there was a time cost as well in terms of hand digitizing even 200 frames for 1 second worth of movement. It was very, very costly. So, but now that we have auto digitizers, and it's a little easier to up the sample rate of our digital world. Okay, so back to analog signals. Analog signals are continuous time functions. Okay, continuous time. Yes, time. Analog. Okay, That's what that is, continuous time function. Digital signal, discrete. Here's my clock, okay? Discrete time, 5, 6, 7, 8, whatever, 3, 4, 5, very discrete. This is digital. And remember, our A to D boards convert our analog signal to a digital signal using some board, some technology that has different number of bits, okay? So the question is, how high should we set our sample rate? Well, what if I set this sample rate to represent this, the time to ultimately over to digital? What if I set it to, well, maybe I want to sample it once every hour, all right? That is, maybe then, I start my data collection at 1 p.m., maybe 6 minutes past 1 p.m. And if I collect the next data point in an hour, well, then the next time I'm going to get is 2:06, 3:06, and so forth, okay? That's supposed to be a squiggly line, all right? That's all the digital data I was able to get by using a sample rate of 1 sample every hour. Now I'd have to convert that over to hertz so I'd have to divide this by 60, so 1/60th of a hertz. It's not a high sample rate, okay? These are the only data points I would get, and I would not be able to represent the fine movements of the analog signal. Well, if I want to represent, reproduce the analog signal in some way from our digital data, I'd have to sample at a pretty high rate to watch this hand move along, okay, and then be able to sample it at different positions, so then I can go and reproduce it. Using the 1/60th of a hertz, I can only reproduce these times from my digital data, right? So there's a link between how much information I get from my data acquisition system, not only from the A to D board number of bits, but also the sample rate, all right? All right, now, to understand sample rates, we have to understand sine waves, all right? I'm gonna draw a sine wave. And I'm going to put time on this axis, and I'm going to put amplitude of the sine wave on this axis. And this is just a positive, minus, and 0. Remember, sine wave is just a continuous repeating pattern that looks like that. All right, let's say this is a continuous time function, and I want to represent this continuous time. I want to represent this sine wave in my digital world. So I want to export the data to Excel, and I want to then create a plot in Excel. Okay, just think of it that way. Well, let's say I sample this data. Let's say this is just 1 second here, just for the sake of. Let's say I sample this data at 1 second. Let's do that. All right, let's say Fs is equal to 1 hertz. That's 1 sample per second. So if I start here, where's the very next data point that the analog to digital data acquisition board would sample? Well, all the way over here. All right, so now I get 2 data points that go to Excel, and I need to create a plot between those 2 data points. I don't see this anymore. All I see in Excel are 2 data points, a 0 where I started, and then the next data point, 1 hertz. Later, 1 sample per second. Now you connect the dots. Well, you can't, right? Especially, well, you can if you know what that signal is, but in the computer world, this is all you know. You only know this data point, and you know those data points, and how can you connect them? You can't. I could draw any path I got, whatever it is, as long as I don't go back in time, I could do that. Even if it was a sine wave, I could even say, well, I'll do a sine wave like that, or maybe a sine wave like that, right? There's no way that without knowing this signal and then taking this and putting it down here, I can't. This is the analog world. This is the digital world. So now 1 hertz doesn't work, okay? Well, sorry, it may work for some things, but for what I'm trying to explain here, I want to reproduce the sine wave in my digital world. That 1 hertz signal didn't work. So let's try again. And I'll just bring up a new piece of paper and I'll draw a new, I'm going to stay with that analog signal, but now I'm going to increase my sample rate. This is still amplitude, positive, 0, negative. Let me get on the screen here. This is still the same time, and this is still the same analog function we're trying to sample. So now let's set up my sample rate. Let's go with 2 hertz. 2 samples per second. Remember, this is 1 second right here. So here I start my data acquisition here. I've got 2 samples to get done in equal time intervals in this 1 second period of time. Well, there's 1 and there's 2. Oh, okay. Well, I've got more data, but did I help myself at all? I don't know. I still need to connect these dots. And if I send you a data set and I say, hey, by the way, here's your digital data for the continuous time function, can you reproduce what the continuous time function looks like based upon these 3 data points? And now I'm saying you don't know this picture. Can you connect those dots without knowing what the original picture was? And the answer is no, you can't, because you still have a problem that you can connect these dots in any number of ways. You'd be forced to use a straight line because you don't know anything else. Anything else, you're just making it up, right? There's no way you can get to that. Now, maybe I say, okay, well, it's a sine wave. Okay, it's a sine wave. It's a sine wave. Okay, well, I could create a sine wave. Yeah, look at that. Oh, there, I'm done, right? No. Sine waves are represented not only by how quickly they repeat, but also the amplitude. And I can have the same sine wave frequency of very different amplitudes. Those are 2 different sine waves. I can do another one here. Now you can start to follow along with me. I can have infinite number of sine waves given those 3 data points. I may have hit the right frequency here. All these sine waves are completing 1 cycle in 1 second, but they all have different amplitudes. All have different amplitudes, the height of the sine wave. So, I still can't get that 1. This is our continuous time function. I'm still guessing. I'm still guessing as to what the data might look like, other than it's a sine wave. All right, but if that's all I know, I still can't reproduce the sine wave. All right, so what do we do? Let's increase our sample rate. So let's do it again. I'll do that here. I'll put time down on the x-axis, amplitude here. And now let's set our sample rate. Well, I could do 4 samples per second. 1, 2, 3, 4. Yeah, I can do 4 samples per second. I could actually do 2.1 samples per second. I could do 2.5 samples per second. I could do any sample rate that's greater than twice the sample rate of the signal I'm trying to represent, okay? So I'm gonna do 4 because I can draw that. I start my data collection, data point here, data point, sorry, let me make that bigger. Data point here, data point here, and data point here. Now, remember, if this is all you know, and I send you data, and I don't tell you anything about the data, and I say, hey, here's the 4 data points, can you create a plot off those 4 data points? What would you be forced to do? You'd be forced to connect the dots with a straight line because you don't know anything else. Oh, that's supposed to be straight. All you know are those 4 data points. But if I told you, hey, by the way, this is a sine wave, okay, it's a sine wave. Well, now you say, oh, it's a sine wave. Okay, well, let me force a sine wave through those data points. And now I can reproduce the continuous time function perfectly, the exact continuous time function, the same continuous time function that I had originally, as long as I had a sample rate that was high enough. In this case, I used 4 hertz. But I also needed to tell you that the continuous time function is a sine wave. Okay. Now, let me see. Gotta keep these straight, otherwise I get them confused when I scan them. 4 and 2. All right. All right. So now, what sampling rate do you need? Well, you need to know what type of information you're trying to record. The sampling theorem is what we use to defend a sampling rate that we use. Theorem. You need to sample, I'm paraphrasing, at a rate greater than, okay, has to be greater than twice the highest, and I'm going to reuse the word frequency here, the highest frequency or the highest sampling rate frequency, highest sine wave frequency that you wanted to detect. Twice the highest frequency that you want to detect. Okay? Twice the highest frequency that you want to detect. That's the sampling theorem, okay? That's the sampling theorem. So in my 1 hertz analog signal example, if the analog signal is 1 hertz, in order to collect all, sorry, I should have added in one more thing, and I'm gonna cheat, and I'm gonna add in it right here. If you do this, what that means is you can successfully reproduce the analog signal. Okay, if you do this, you can successfully reproduce the analog signal. If you don't do this, you cannot be successful. So we want to be successful. So collect that all together is the sampling theorem. If you sample it twice at a rate greater than twice the highest frequency that you want to detect, you can successfully reproduce the analog signal. So if my analog signal is 1 hertz, I just need to sample at anything greater than 2 hertz. 2 hertz isn't going to cut it, all right? That's not going to cut it. We looked at that. That's going to end up with a straight line, All right, but to get to be able to reproduce this 1 hertz signal, I need 2.1 hertz. I need 2.12 hertz. I need anything greater than twice the rate that I want to be able to detect. So let me just show you. This is what I'll try to draw it. I won't do a great job with it. But if I know I'm trying to reproduce a signal here, a frequency, a sine wave, then if I have data points that are at a rate greater than 2 hertz, I may get these 3 data points. Oh, now I got to try it. This is not going to be easy. I may have already messed up. All right, I got to force the signal through those data points. Excuse my artwork, but that, if as long as I have data points that are happening at a rate greater than twice the 1 hertz, I am reproducing this signal. So what I'm trying to do is draw a data point here, a data point here, a data point here. That still has to be equal intervals. They're just happening at a rate faster than 2 hertz, okay? Faster than 2 hertz, 2 samples per second, which would have been 0, 1, and that. 0, here, and here. Something greater than 2 hertz would be here, then maybe about here. And once you have those 2 data points, you can only fit 1 sine wave through those data points. That's what I'm trying to draw there. Just not, I didn't do it as even as I should have. So excuse the poor art. Okay. All right. So I need to record it at greater than twice 1 hertz. 2 hertz isn't going to cut it. Okay, 2 hertz will not cut it because I get this data point, this data point, this data point, and I can do all sorts of amplitudes. I get the same frequency, but I don't know which one actually is the continuous time function. So that's the sampling theorem. So another term that we use when we talk about sampling rate is the Nyquist, Nyquist frequency. I was going to write sampling rate, and I was thinking ahead. Nyquist frequency. Sorry, I'm going to get irritated if I got that little box there because I am going to upload these notes. We'll do it again. Nyquist frequency. Well, now I can't spell it. Frequency. All right. The Nyquist frequency is the frequency equal to twice the highest frequency in the analog signal, okay? So that's why sometimes you'll hear people say Nyquist sampling rate, okay? So it's twice the highest frequency in the analog signal. Okay, now my brain is also thinking ahead and I need to explain what that means. But right now we've got a continuous time function of 1 hertz. All right, that's the one we're working with right now. The Nyquist frequency would be 2 hertz. The sampling theorem would tell us we need to sample at something greater than 2 hertz in order to reproduce the continuous time function. Okay, so that's why I actually don't like this phrase here. Okay, when we're in the lab, the Nyquist frequency represents 2 times this frequency. The sampling theorem tells us we need to sample at a rate greater than the Nyquist sampling frequency. Okay, so I don't like this phrase in when we're talking about what sample rate to use for a signal. All right, so now what you are probably seeing at this point is that I'm really talking about the minimum sample rate needed to represent this signal, okay? The minimum sample rate is anything greater than 2 hertz. So I showed you 4 hertz. But what do we typically do in the lab? We may sample at 1,000 hertz, all right? Why do we sample at 1,000 hertz? Someone's got to remind me to remember these. Why do we sample at 1,000 hertz? Well, if I go back to my analog signal of 1 hertz, remember, even 4 hertz, we were able to get these 4 data points, and then we could say, oh, in Excel, I can trick Excel. I needed to know it's a sine wave, and I can fill that in with a sine wave function and force the sine wave through those data points, right? But man, that takes time, right? So this is FS of 4 hertz. This is a signal is 1 hertz, just for sake of example. Well, I'm lazy, okay? I don't want to have to work the magic in Excel to do that. So why don't we up that sample rate to 1,000, okay? A number that we typically use to record ground reaction forces. All right, so now what I'm going to do is sample 1,000 data points in this 1 second. All right, 1,000 data points. Let me start. All right. 1, 2, 3, 4, 5, 6, 7. Okay, yeah, that's going to get boring, right? But these are all the data points that are going to be collected and more because I'm not doing them all. All right. All right, this is, come on, let's get to the curvy part there, back up here. Okay, boom. Wow, that looks a lot like the continuous time function. So it's a super easy way to represent the continuous time function in the time domain, okay? In the time domain. And I should define that. Time domain is anytime we have a plot with time on the x-axis. Time on the x-axis, okay? Anytime we have time on the x-axis. So in the time domain, this signal, the continuous time function, in the digital world, remember this is digital, and this is analog. The digital signal looks a lot like the analog signal. And it's super easy now to say, oh, that's a 1 hertz signal. Oh, shoot, I messed that up. That's a 1 hertz signal, okay? We connect the dots in Excel and we create a nice plot and say, yeah, okay, I'm pretty confident that was a sine wave, okay? Because I sampled at 1,000 hertz. I didn't need to. As per the sampling theorem, I just needed to sample at something greater than twice this. 4 hertz would work, but I need to know the sampling theorem tells me that I can reconstruct the signal when I sample at a rate. And when I reconstruct the signal, what I'm actually doing, and we'll talk about this in another video, what I'm actually doing is reconstructing the signal based upon sine wave information. And so I know that these data points are represented by a sine wave. So I already know that ahead of time. So the sampling theorem tells you you can reconstruct the signal when you have all the sine wave information necessary in that signal. And you need to therefore know the highest frequency that you're trying to detect. And then the Nyquist frequency is twice that. And your sampling rate needs to be just greater than that Nyquist frequency in order to do this, okay? All right, now, but 1,000 hertz, this has nothing to do with Nyquist, other than this is well above, this is 1,000 times faster than our analog signal. Why do we use 1,000 times? Because one, it's cheap. You know, digital data now is so inexpensive. Um, Film data, if we're doing film, that's still a problem. Uh, Video data, it can still be a memory problem if you get a high-speed camera and you're recording video images at 10,000 hertz, 10,000 frames per second, or 1,000 frames per second. That's a lot of memory that you gotta, and it takes a lot of computing power, right? So that can be a problem. But for you know, our ground reaction force data, or maybe our acceleration data, that's actually not too expensive to collect 1,000 hertz. Now, why not 10,000 hertz? You're probably going to get the same thing. And a great exercise I love doing in instrumentation is actually going down and taking a signal, a ground reaction force signal, and then down sampling it from, you know, start at 10,000 hertz and then resample it at 5,000, 1,000, 500, 250, 150, 100, you know, 25, whatever. And you start to see how the signal changes. If you're in the lab and you want to try that, that's a great thing you can do in Fireware. You can actually set it not only to collect at a high rate, but then you can also resample the data in Fireware, and you can downsample it. You can't, I don't think Fireware upsamples, but you can downsample it. All right, so if I'm lazy and I don't want to reconstruct the signal, meaning I need to do something in a frequency domain, which I'll do in a separate lecture. If I don't want to do that reconstruction of the signal, I just sample the analog signal at a really high rate, well above the highest frequency that I'm trying to detect. Okay, trying to detect. 1 hertz, I'll sample at 1,000 hertz. Okay, as long as it doesn't cost me anything, because I'm pretty cheap. As long as it doesn't cost me anything, then I'm pretty good with that. All right, so my watch, my GPS, where'd it go? My GPS watch samples at 1 hertz. That means the highest frequency content it can detect is just under half of that. So half a hertz. Okay. So I'm not getting real continuous time data with this watch. Okay. But I am getting some other information that at an appropriate rate and that I can reconstruct in order to get things like stride rate. Okay. Okay, I think that's it for this one. At some point, I'll add in a frequency domain lecture. Okay, thanks.